Oh, Brandon, you're in a summer with a summer uniform today. Isn't it too early?
It's nice outside. It's like 50 degrees.
I don't know.
It's just really cold in your classroom.
Well, on the other hand, the weather forecast seems to be military secret, right? Julie? So didn't we disclose something? Right?
Just yourself back to 100%. This is really good for me.
Okay.
6 points for not having
Time to get going. Oh, it's this time. Okay. Okay. So, chapter 29 is the first chapter of modern physics, and it is mostly description of the main results obtained in the last probably 100 or so years. And the first part of the chapter is a description of several experiments that require you to treat the light either as an electromagnetic wave or as a stream of particles. So we already talked about the double slit experiment with light. So if you have two slits separated by appropriately selected distance, and if the incoming light is, let's say, monochromatic with wavelength lambda, you know that on a distant screen, you're going to observe typical interference pattern, I guess. Well, you're going to observe the same interference pattern if you do the experiment not with light, but if you do it with sound waves, or if you do it with surface waves on water. You observe pretty much the same interference picture. The only difference is that you have to select the distance and the size of the slits appropriate, consistent with the wavelength of the waves that you work with. So the double slit experiment and similar other experiments related with diffraction or interference are a proof that the light has a wave nature. It has to be considered as an electromagnetic wave. Again, waves are patterns of something that propagate in space with certain speed and also carry energy and momentum and angular momentum. Keep also in mind that instead of talking about wavelength of the wave, you can talk about the frequency of oscillations of the wave. And the two are connected, right? The frequency of oscillations is the speed of light in the case of light propagating in vacuum divided by the wavelength. And now in the textbook you have a description of 3 different experiments, again, experiments done with light, which cannot be explained if you think about light as a wave. So historically, the first experiment of that type is the black body radiation spectrum. So what does this mean? Well, it sounds very fancy, but it is something very simple. If you take any material and start heating it up, at some point you're going to see it is going to start emitting light, right? It is going to get red hot first and white hot if you increase the temperature further. In other words, the color of emitted electromagnetic waves, the wavelength of the emitted electromagnetic waves, depends upon the color of the object. And, well, you can say, here is an object, and you see that at room temperature, this object is emitting red light right here. And of course, this object is at room temperature. There is something wrong in the description that I just gave. If I warm up this object or cool it down, this button is still going to be red. Well, the reason for that is, of course, that the material this button is made of reflects very well red light, red wavelengths, and absorbs the other wavelengths that come from the sources of light around us. This is the reason why it has this specific color. So in other words, in order to do an experiment that shows a connection between the temperature and the emitted light, you have to get rid of the colors of the object itself. In other words, you have to make this object not to emit any light. Any light that hits it is absorbed and no light is reflected. Everything is absorbed. Objects like that you perceive as black objects. So this is why we're talking about emission of light from black body. Well, you can say, well, do black bodies exist? Well, clearly this piece of plastic here is black, but it is black only in the visible part of the spectrum. It may not be black in the infrared. So if you put night vision goggles, infrared vision, maybe this object is going to be shiny, not dark. So you need an object that is absorbing any light that hits it, any frequency, visible or invisible part of the spectrum, electromagnetic spectrum. And a standard way to achieve this type of absolutely black body object is take a cavity. Here it is a cavity with a very small opening in it, so that any light that comes in through the skull, eventually it is going to be reflected multiple times, but it is very unlikely that this light ray is going to go back and get out of this opening. So an observer that looks at this very small hole is is going to see a black color, pretty much, if the hole is small enough. In other words, this object, the inside of this object is a black body. And the next step is, once you have a body that is really black for all wavelengths, the next thing is to figure out how the colors of this black body change when you start changing the temperature of this object. So just take this object and start heating it up, and at the same time observe what you see here from this small hole. Again, when the temperature reaches, let's say, something like 1,000 or 1,500 degree Kelvin, you're going to see that this hole is going to emit visible light, probably initially red. Later on, if you keep increasing the temperature, the color is going to be white, and so on. Yeah.
So if you were to shine a laser into that black hole and it's or a black body, wouldn't it reflect to the point where you could see that visible light?
Well, so if you directly have a light coming in this way, well, you can always make the hole small enough so that, well, it is very difficult to get exact reflection exactly back. If the hole is small enough, you're probably not going to get reflection. And in the case of laser, at least, you can always make sure that the inner walls of this cavity are black. And whatever you shine, it is just going to be absorbed and not going to come back to you. But again, well, of course, absolutely black body is an abstract concept. It is difficult to imagine a situation in which you have absolutely black object. But this is a very good approximation of a black body. And again, you start heating it up, and you look through this small opening, through this small hole, and you observe the colors that you see as a function of temperature. What you're going to see is that the spectrum of the light emitted from this black body is, of course, going to be temperature dependent, but at some temperature, the intensity of different wavelengths, let's say, well, let's do frequency, or no, let's do wavelengths. Well, frequency is better. And this is intensity of light with this particular frequency. So what you're going to observe, let's say on temperature 2000 Kelvin, would be a spectral picture like this, let's say. This is for temperature 2000 Kelvin. Well, if you accept that the light emitted by the walls of this black body, that light, if you treat it as electromagnetic wave, you can never figure out the shape of this spectrum. All calculations are going to be able to reproduce the spectrum maybe for low frequencies, let's say, or for high frequency. So you're going to be able to calculate roughly the infrared maybe, and maybe the ultraviolet emission. But the rest of the spectrum is not going to be calculable if you treat the electromagnetic waves as waves. If you treat the light emitted by this black body as electromagnetic wave, you cannot reproduce the spectrum. And this was a problem in early 20th century physics. So people tried to figure out how to calculate this color, this spectrum emitted by a hot black body for probably a few decades with no success. So this was one of the unresolved problems in physics. And of course, the solution to this problem, in a sense, came just with a simple mathematical trick. So the solution was obtained by assuming that the light inside this black body, the light that eventually you're going to observe, is carried in small portions. Each of those small portions of energy carried by the light is proportional to the frequency of the light. So the total energy emitted by this hot black body is integer number of these portions of energy, integer number n. So the total color of light with frequency corresponding, let's say, to red, is going to be some integer number of a constant h times the frequency of the red light. Here, n is integer number, 1, 2, 3, and so on. H is one of the three universal constants of nature called Planck's constant, with numerical value in SI units equal to 6.6 times 10 to the negative 34 joules times seconds. So this solution of the black body spectrum problem was offered in early 20th century by Max Planck. And he considered it initially as a purely mathematical trick to get the right answer, to get the answer that is consistent with the observations. And a few years after this proposal, people gradually realized that this simple formula describing that the energy of the light emitted by this object is only carried in portions, people gradually realized that this formula actually describes the energy of n photons. Each of those n photons carries energy. One photon is with energy Planck's constant multiplied by the frequency of the light corresponding to a particular color. In other words, this mathematical trick in reality was a description of the light emitted from this black body, not as electromagnetic wave, but as a stream of particles that now we call photons. Each of the photons emitted from this hot black body carries energy h times f, and depending upon how many photons you have in the stream of photons, you observe one color or a different mixture of colors. So for a black body with temperature about 2000 Kelvin, most of the photons, so largest number n, happens to be in the visible part of the spectrum. But of course, you have some photons that have lower energy, infrared radio wave, microwave photons, and you may have a small number also of photons with higher energy corresponding to UV, let's say, part of the spectrum. And of course, if you increase the temperature of your black body, the black body spectrum shifts to higher frequencies. So maybe for frequency of the order of, for temperature of the order of 4000 Kelvin, if your black body doesn't completely evaporate, most of the emitted photons are going to correspond to electromagnetic waves in the, let's say, X-ray part of the spectrum. You're still going to have some photons in the visible part of the spectrum, but you're also going to have larger number of photons in X-ray part of the spectrum and higher frequencies. Yes.
So the equation with the integer n is when light is in a wave, right? Versus when light is specifically in a photon.
So look, you definitely should have, if you read the chapter or if you listen to what I'm talking about, you must have so many questions that we wouldn't be able to answer until the end of semester. Because the concepts that I'm describing are quite counterintuitive. So they actually are in clash with our, as you're going to see, with our classical understanding and classical intuition. So here, the number n just means that the energy of carriage is the energy of, let's say, photons with frequency corresponding to, let's say, red part of the spectrum is proportional to this number of photons. So each photon has energy h times f. You have, let's say, 1000 or 1100 photons with that particular frequency, that particular color. And therefore, you're going to see light that has intensity in the red part of the spectrum proportional to the number of photons. So if you have a different frequency, right? So let's say the F here is maybe something like red part of the spectrum, maybe here, red part of the visible spectrum, and maybe equal to 1100 photons with this particular frequency, with this particular color. However, this black body also is going to emit photons with energy hf prime, where f prime may be corresponding to the blue color. And maybe in this formula for temperature 2000, n prime is going to be 2000, let's say, or 2200. This means that the same black body also emits blue photons, and they're more than the red photons. And therefore, the color that you're going to observe is going to be more bluish than reddish. It is going to be a mixture of those, but with higher emphasis on the blue color. So this this assumption that the energy in the light emitted by this black body only can be in portions, integer portions, indicates, and you cannot have half a photon. You either have integer number or zero. You cannot have fractional numbers of photons, which is a typical property of particles. Right? You cannot have half an atom, right? You cannot have half an electron. So this historically, this black body spectrum was the first indication that the light should be considered as stream of particles. And there were two other experiments that were done around the same time, early 20th century, that also required interpretation of the light as a stream of particles. So the first experiment of that type was, well, the easiest to describe experiment of that type was the so-called photoelectric effect. And it is something very simple. Let's say that you have metal surface right here, and you remember that metals have large number of electrons in them that are almost free, easily moving. Still, those electrons are attached to the metal. It takes some energy to take them out of the surface of the metal. And the photoelectric effect is an effect of emission of electrons from the surface of a metal if you shine light on this metal. So what if you shine light with appropriate frequency, with appropriate color, you observe that electrons are emitted, and those electrons are going to be moving, let's say in this direction with velocity v. In other words, they carry, let's say, kinetic energy, 1/2 the mass of the electron is squared, non-relativistic. So if the incoming light has frequency f, you observe this emission of the electrons. Now, if you try to interpret the photoelectric effect as if the electrons have been removed from the metal from electromagnetic waves, you encounter problems. The first problem is that the experiments show that the photoelectric effect occurs almost instantaneously. As soon as you shine the light, you observe an electrons emitted from this metal. There is no delay. While if you treat the light as electromagnetic wave, the calculations show that the electron on the surface of the metal is gradually going to start oscillating with larger and larger amplitude. And at some point, the amplitude is going to be sufficient to free this electron from the metal. But the calculations show that this emission of electron has to occur after some time interval and not instantaneously with the shining of the light. So this was the first difficult to explain property related with the photoelectric effect. The second property was that there is a cutoff frequency. If the frequency of light is below certain threshold, let's say if the light is red, you don't observe photoelectric effect. No electrons are freed from this metal. You need frequency higher than certain threshold. let's say for certain metal, you need frequency corresponding to blue light. Red light is not going to do it, no matter how long you shine it. Again, if you think about the light as electromagnetic wave, even a low frequency of that light is gradually going to increase the amplitude of oscillations of the electrons that accept that light, and eventually some electrons are going to be emitted from the surface, which doesn't occur if the frequency of light is below the threshold. So another property of the photoelectric effect that cannot be explained if you think about the light as electromagnetic wave. And finally, another property that is also unexplainable from classical point of view is that the intensity of the emitted light doesn't affect the kinetic energy of the emitted electrons. So you can shine even a small amount of light with frequency above the threshold is going to do the job for you. But larger, more bright light is not going to allow you to see higher energy of the emitted photons. You're going to see a higher energy of the emitted electrons. You're going to see more electrons, but all of them are going to have pretty much the same energy. And the experiment shows that the energy, kinetic energy of the emitted electrons is going to be equal to the energy of a photon minus a small work function, which depends upon the nature of the metal that you're shining light on. So this work function W is the amount of energy needed to free an electron that is already on the surface of the metal, to free it from the metal, to free, to get it, to allow it to move out. So this formula, this simple formula, tells you that there is a cutoff frequency. Remember, kinetic energy has to be non-negative number. So in order you to see an electron emitted from the surface, the energy of this photon has to exceed the work function. In other words, the frequency has to be larger than what the work function, to overcome the work function for this particular metal. In other words, frequency below certain frequency is not going to be able to satisfy the need for work to extract the electron, and therefore you're not going to see electrons emitted from the surface. So this simple formula, it was proposed in early 20th century by Albert Einstein, and this is the formula that gave him the Nobel Prize. Not the relativity, not the special or general relativity. And of course, this formula exactly describes the experiment. And of course, this formula basically says that what is happening is that a photon hits an electron, and if this photon has sufficient energy, that electron just is going to be able to leave the surface of the metal. Okay, any remarks, any issues about black body or, yeah?
So when you're talking about frequency, again, you're talking about the constant C divided by the wavelength of the light.
Yes. So frequency and wavelength are pretty much the same.
They're inverse of each other.
They're inverse to each other, but they describe, in the case of visible light, they describe the color. That's it. So there are two different ways to describe the same thing, the color of the light that we see. If it is visible, if it is invisible, they describe wavelength or frequency of this electromagnetic wave.
And what is the work being done by? What is doing the work?
So here is what's happening. The photon here is one electron close to the surface. I'm not going to draw the surface of the metal. The photon comes, hits it, and gets absorbed. So it is, in a sense, completely inelastic collision. What is this electron going to do? It's going to recoil. And it is going to recoil with some kinetic energy. Well, you have to spend some energy to get free from the surface of the metal. And that energy is what we have here, so-called work function, W. And it is a number that is tabulated for different metals. So in the homework assignment, you have questions where you have to use this formula. But if you were born 100 years ago and you used this formula, you were going to get $1 million or so for a Nobel Prize. Well, at that time, the Nobel Prize was less than $1 million, I guess. But yeah. Okay, any other remarks? And one more experiment that requires interpretation of light as a stream of particles. It's very similar to photoelectric effect, but so-called Compton effect. It is pretty much the same situation. You think about electrons on the surface, usually of the metal. And if you shine appropriately, let's say, wavelength, light with wavelength lambda, or corresponding frequency, but for this description, I prefer to work with wavelength. You have a collision between a photon and electron. But now the collision is not completely inelastic. Now you have a recoiled electron coming, let's say, this way. And you have a recoil photon with different frequency, with different wavelength, lambda prime, going this way. So it is just like a collision between two objects. Now, let's say that this recoil photon goes, let's say, this way. It's the recoil photon with frequency with wavelength lambda prime. The angle between the original direction of the incoming photon and the recoil photon, this angle is angle theta. And if you write conservation of energy and conservation of linear momentum, exactly like we did in chapter 6 or 5 the first semester for the case of collision between two objects, two material particles. If you write energy conservation and momentum conservation, you are going to see that the wavelength difference of the original and the emitted light, which you can call delta lambda, the change of wavelength, is described with a constant of proportionality times 1 minus cosine of the emitted angle theta. And the constant of proportionality happens to be Planck's constant divided by the mass of the electron and divided by the speed of light. This is a practically classical calculation which assumes that the photons have carry energy E of one photon, h times frequency, or h times, instead of frequency, you can say c divided by lambda. Just like two balls colliding and flying in some different directions, colliding elastic. So you cannot explain the photoelectric effect, and you cannot explain the Compton effect if you think about light as electromagnetic wave, as wave. You have to think about light in terms of particles. So which is the correct description? Is light a stream of particle, or is it electromagnetic wave? Wave or particles? What is the correct? Yeah, David? David, right?
Dane.
Oh, Dave. Dave.
Is it a wave? No, wrong answer. It's particles.
Look, when I ask a question like this, there is no wrong answer.
Oh, dang.
Well, in the textbook, they say it is wave-particle duality. So, but look, does it make sense? Right, so, is this on the screen a cat or a dog? Well, you can say it is cat-dog duality, but it is not going to make much sense to a person with normal reasoning. And this is one of the unremaining unsolved problems in modern physics. Well, to make the things even more strange, look, this is the proof that light is a wave, electromagnetic wave. Now you do the same experiment, but choose appropriate distance between the slits and the size of the slits. And instead of light, you can start, you can have a beam of particles, let's say electrons. Electrons clearly are particles. You have seen them, we work with them in electronics all the time. What do you see after this beam of electrons goes through the slits? You would expect to see electrons hitting here, and no electrons hitting in the middle. But in reality, if you select the distance between the slits appropriately, you're going to see exactly the same interference picture as you saw with light. Therefore, you say, well, it looks like electrons are waves. You do the same experiment also with other particles, let's say neutrons or protons or even larger molecules. If you choose the size of the slits and the distance between them appropriately, you observe interference pattern. You can do that experiment even with almost macroscopic objects. You can do it in a sense with pieces of chalk. You start throwing them against those two slits with appropriate size and appropriate separation, and you're going to eventually observe interference pattern. Of course, in practice, the size of the slits and their separation is such that you cannot manufacture such a diffraction grating, such a slit system of slits. If you want to do the experiment with pieces of chalk. So, but in general, theoretically, the same observation holds. So is this piece of chalk a wave? Does it look like a wave? No, it is a particle. Well, what is the wavelength of this piece of chalk, if you think about it in terms of waves? Well, people somehow guessed the answer, and the answer seems like this. The wavelength of this piece of chalk is equal to the Planck's constant divided by the magnitude of the linear momentum. Recall that linear momentum is mass times velocity. So if you have small linear momentum, the wavelength of this particle is going to be large. If you have large momentum, this chalk is moving fast, you're going to have shorter wavelength. But in any case, manufacturing of a two-slit system with appropriate size is not technically doable. Okay, so in other words, it looks like in certain situations, you can treat objects as if they are particles. In other situations, it is more convenient you to treat the objects as waves, electromagnetic waves or waves of different quantum nature. So next time, actually, we have practically everything that you need to answer the homework problems, except the Heisenberg uncertainty relation that we're going to talk about next time. So please take a look at this chapter. You should, if you read the chapter, you should have so many questions that we cannot answer all of them until the end of the semester. Yes.
When will we get our test back?
Oh, yes. So one version of the test is graded, but not the other version. And I'm going to check with the grader. I hope that I haven't seen him. So by Friday, you should have the test back. And well, at least you, Brandon, you aced the first two tests. So for you, it doesn't matter because we're dropping the lowest midterm, but I'm sure that this midterm was also good. Actually, most people in this section of the class are doing very well. So the test again is going to be, so better focus now on the final exam, especially chapter 27, interference and diffraction. It is more trickier chapter. And the chapter 29, this chapter, you have only two formulas, actually. Only this and this, maybe this one, and the Heisenberg uncertainty, but those formulas can be used almost just by plugging numbers in the equations and getting the answers.
Does the final also include like stuff from the beginning of the semester, resistance?
I'm going to give you directions about the old chapters so you not to be overwhelmed. But all conceptual questions are going to be fair game. For the calculational questions from the old material, I'll give you some directions so you not to be completely overwhelmed by different